Have you ever wondered how our sun affects the planets in our solar system? Did you know that the sun emits a stream of charged particles that constantly flows outward, affecting everything in its path? This phenomenon is known as the solar wind, and it has a significant impact on the planets in our solar system. Join us as we explore the fascinating world of the solar wind and its effects on planets, and also on Earth. What are the solar winds? The solar wind is a flow of particles that comes off the sun at about 1 million miles per hour and travels throughout the entire solar system. First proposed in the 1950s by University of Chicago physicist Eugene Parker, the solar wind is visible in the halo around the sun during an eclipse, and sometimes when the particles hit the Earth's atmosphere, as the aurora borealis or northern lights. While the solar wind protects Earth from other harmful particles coming from space, storms can also threaten our satellite and communications networks. The impact of solar winds on planets. The ionized particles in the solar wind are coupled with the solar magnetic field to form a spiral structure in space known as the Parker spiral. These high-energy solar wind particles cause aurora on planets with a magnetic field, but they can also be disruptive to planet atmospheres and surfaces. This rain of plasma particles can collide with particles high up in a planet's atmosphere, giving the atmospheric particles enough energy to escape a planet. This is called solar wind stripping of an atmosphere, and may have been partly responsible for the dramatic change in the atmosphere and climate on Mars. Space weathering caused by solar winds. Solar winds also cause space weathering on airless bodies like Mercury and most of the moons in the solar system. Space weathering can cause some substances to vaporize from the surface or cause other particles to become fused. For example, the top coat of regolith on the moon is much darker because of extensive space weathering. Dangers of geomagnetic storms caused by the solar wind. The solar wind becomes most dangerous to Earth during a solar storm. Much of the plasma in the sun's corona is typically confined in regions where the sun has strong magnetic fields, like in the sunspots. Here, the magnetic fields create large arcing loops over the plasma, like a net holding a fish. A coronal mass ejection is a plasma storm that occurs when those magnetic fields experience reconnection events that realign the magnetic fields. After a reconnection event, there is a big hole in the net, and solar plasma can explode out of it. This explosion causes a much bigger mass of plasma than usual to be hurled through the hole and into space. Sometimes that plasma is directed towards the Earth. If so, the huge flood of ionized particles can disrupt our magnetosphere and cause new currents to flow. We call this a geomagnetic storm. Radiation from these events can cause the aurora to appear at lower latitudes than it normally would. And not only are aurora pretty, but the light signals can also offer us hours of early warning for the massive plasma to come next. Electrons and other charged particles from geomagnetic storms can also disrupt electronics, including radio transmissions and satellites. For example, GPS coordinates can stray by several meters during a storm. It might not sound like much until you realize that planes land via GPS. Other dangers of solar storms. One concern for long-time space travel is the effect of solar storms on astronauts. A solar storm hitting a spacecraft would result in severe exposure to high-energy radiation by the astronauts, maybe enough to be fatal. So this will be a rare but important obstacle when trying to plan human voyages to Mars or further. The breakthrough discovery reshaped our picture of space and the solar system. Scientists came to understand that the solar wind not only flows past Earth, but throughout the solar system and beyond. It also both protects and threatens us. The solar wind magnetically blankets the solar system, protecting life on Earth from even higher energy particles coming from elsewhere in the galaxy. But it also affects the sophisticated satellite communications we have today. So understanding the precise structure and dynamics and evolution of the solar wind is crucial for civilization as a whole. Since the solar wind fills the space between the planets, it is important to know its main characteristics when we want to travel through this environment with spacecraft. The solar wind is a determining factor for the immediate environment of the Earth. Fortunately, our Earth has a magnetic field that can stop the biggest part of the charged particles of the solar wind. Yet, some of these particles can enter the atmosphere, where they cause, for example, polar light. Solar wind storms cause power failure and satellite breakdowns. Once-in-a-while storms also occur. In 1989, as a consequence of such a storm, large parts of Canada and the United States experienced a major power failure. Variations in the solar wind cause electric storms and corrosion in the many kilometer-long pipelines of Alaska. Storms disturb radio transmissions, and also space travel has to deal with certain consequences. The charged particles of the solar wind can be compared to radioactive radiation. It isn't the first time that a satellite breaks down due to intense radiation during a storm. Weather in equatorial areas related to solar wind. Daily changes in weather in equatorial areas. During the daytime in equatorial areas, where solar irradiation occurs directly from the front, the wind is characterized by a clockwise flow as solar wind enters the upper atmosphere. In contrast, the solar wind drives the counterclockwise flow of the atmosphere at the night side. Therefore, rain occurs in the evening along the equator. Madden-Julian oscillation, MJO, is a weather phenomenon in the equatorial region, generated in the western Indian Ocean, wherein alternate wet and dry areas move eastward with a slow repetitive cycle of approximately 1 to 2 months. The slow speed at which weather migrates east over a wide area in the tropics can be understood as an effect of solar wind. The counterclockwise flow of the atmosphere at nighttime is offset by the effect of trade winds blowing from east to west. Mechanism of typhoon. Typhoons occur in the Pacific Ocean during summer in the northern hemisphere. The most irradiated region during the summer solstice is around the northern latitude of 23.4 degrees. In this area, although trade winds blow in the daytime, at the end of June, westerlies of counterclockwise direction blow on both sides of the trade wind. Since the Earth's axis of rotation tilts at 23.4 degrees, the solar wind has a moving component in the north direction. So, when water vapor uprises at the southern region of the trade wind blow in the summer, that is the region where the westerlies wind blows, the vapor of water moves northwest with counterclockwise rotation and collides with the trade wind of clock rotation. The collision forms an anticlockwise vortex. In conclusion, the study of the solar wind is an exciting and rapidly evolving field of science that has important implications for our understanding of the universe and its effects on planets like Earth. The solar wind is a powerful force that shapes the environment of our solar system and plays a crucial role in the development and evolution of planets. By studying the solar wind, we gain valuable insights into the processes that have shaped our planetary neighborhood and how they continue to shape it today. If you found this video useful, share it with your family and friends, and also subscribe to our channel.